Okay guys, hello and welcome back to our tutorial on timers, lesson number 16. We're going to be looking through how to actually code this now. This is going to be the coding portion. So again, our hardware schematic here, we've got our LEDs and basically everything else just normal in place. We've got our regulator and our pull-up and everything. So let's get started. I also want to introduce to you guys a new IDE. Well, it's not really new, but it's fairly new, and I've waited for it to kind of seemingly get more stable that Microchip has produced. But the IDE is going to be the Mplab X Ide. You can download this again from Microchip. What's nice about it, those of you other coders that are out there, it's based off of the NetBeans coding interface, which I don't know if you guys are familiar with NetBeans, but NetBeans is a great IDE for pretty much any type of embedded software, just software development. Here's the web page on it. But NetBeans is very good. It's based off of the Eclipse IDE, which was kind of one of the first ones, and it's very good. It's very useful. You can customize everything, clear down to the colors of everything. You can customize the way that its appearance, the way it searches, the way it does everything. It's kind of a lot better tool. I really applaud them for making the switch. So what we're going to do is we're going to start a brand new project. And when you start a brand new project, you're going to do ours. We're going to do a stand. You can even import your existing version 8 IDE projects if you want to. It's kind of nice. I'm just going to do a regular standalone guy. So we're going to go next, and we choose from our families list. We're going to choose our mid-range, baseline. Sorry, 676 is a baseline. And then we're just going to type it in. Pick 16F676. Okay, I was wrong. I'm getting some beeps here. I'm wrong. It is a mid-range. 676. Alright, there it is. Okay, 676. That chooses our chip. Next. We can do debug headers. We don't need to do any, so just skip it. Here's where you get to choose what kind of tools, hardware tools you're going to be playing with, or any kind of starter kits or whatever. I have an ICD3, so mine shows up here. It even shows the serial number of it. So that, and here's where you get to choose your compilers. Now for this one, I'll probably come back and do it the other way, but I've started really playing with the high-tech compiler. I know a lot of you have requested that I mess with the high-tech compiler just because it's free. It's free to download. You can download it and play with it. It's got a light mode, so it can only compile so much code, but for simple little, just playing with projects and simple little projects you guys want to do at home, it's a really good compiler. The difference that I saw, that's a huge difference between the two. There's pros and cons to each one. The high-tech one, the pro to it is an ANSI standard. The American National Standards Institute, or whatever is what ANSI stands for. Hopefully I did that. Hopefully I said that right. But it's an ANSI standard compiler. So all the different keywords and everything like that, and the way you do the formats and everything of the compiler match all ANSI standard compilers. So that's one thing that is very nice about that. However, CCSC is not an ANSI standard, which means that they kind of have, and they have some of their own kind of little keywords that they've made that really don't follow a standard. So that is one plus to the high-tech PIC-C, high-tech C compiler. Another plus to the high-tech PIC-C compiler is that you can embed. I don't know now. Don't quote me on it. Those of you, you can make comments if you want, if I'm wrong. But I don't believe there's a real good way to embed assembly language inside of the C code. With high-tech C, you can do that quite easily. I think it's just a pound ASM, and then you start, you're done, and then you do like pound end, I think, end ASM, I think. I don't know, I'd have to look at it again. But you can embed assembly code right into it, which is another thing that's nice. Also, high-tech C it can also has a lot more Register control, one thing I noticed that is very nice is that when you look up in your data sheet and you see like, oh, for example, our timer 0 interrupt flag is T0IF is what Microchip abbreviates it in their data sheet. It's T0IF for the timer 0 interrupt flag. It is exactly the same. That abbreviation is exactly the same for the high tech. So if you want to read that register, you want to read if it and see if it's 0 or 1, if it's set or cleared. You just type in, like an if statement. You type if, T0IF equals 1 or 0, Whereas with CCSC, I think it's like TMR0 I or something like that, or I don't know. It's completely different. And so that is another plus, is that the data sheet and high-tech C will coincide with each other. So that is another plus. The plus to the CCSC compiler, they have tons, and I mean tons, of pre-built code for you. Pre-built libraries, pre-constructed libraries, examples, tons and tons and tons of examples on pretty much like everything the controllers can do almost. I mean, just everything. Like timers, they'll show you how to configure every single kind of timer, whether it be real-time clocks, timers, timer 1, timer 0, 8-bit, 16-bit, 32-bit. I mean, they do it all. If you want to incorporate watchdog timers and everything, and they have example code for all of it. So that is one nice thing that is very, very nice about CCSC, is that they may not follow a standard, they may not be perfect, but they have tons of examples to help you out. So that is a very big plus of the CCSC, and why I started off using the CCSC compiler when I first started this, because it was a very easy tool to just, kind of, if you're a beginner, don't really know too much, you're sort of good at software, not real great, the CCSC, you can just pick it right up. If you know any little bit of C, you can just pick it right up and go. High-tech C is a little more involved. It's a little more, you got to really read the data sheets and really dig through the data sheets and find how to control your device and like I said, line up those keywords. But anyway, one good thing is high-tech C is free. Pixie and CCS is not. So we're going to, this first go around, we're going to do high-tech C. So we're going to add that. So our project name, we're now going to have, we're going to just call this lesson, 16 firm. So we're going to call it, why not, finish. Okay, so that builds our project. Now we're going to have to add some files to it. So here's our kind of hierarchy up here, our project. So we've got header files, source files, object files, all that stuff. We need to add a source file to it. So what we're going to do is we're just going to call it a source file. We're going to call this, we'll make this our main. If you do main, you can do main, but main will have pre-built stuff in it, and usually it's kind of it's pre-built stuff that it's kind of guessing at what you're gonna do. So I just do a regular, I'll say lesson 16 main, TMR main, finish, and then we just get a blank page and we can put our stuff in. So those of you that have played with this before, we're going to put in our include htc.h, and then I have my colors set up like this. You may set up your colors different. I don't know why this is telling me this is wrong. Interesting. Oh well. Anyway, okay. Sorry, I'm getting sidetracked here and wondering why that's doing that. Alright, the next thing that we're going to do is we're going to put some defines in. We're going to define a few different things. And what I'm doing is I'm going to go off of the example that they give you, the timer example. And in fact, what I'm going to do is I'm going to just grab some of their code and just slam it in here for time's sake, because I know this video is probably already really long already. So I'm slamming this in here. Alright, what they're doing is they're defining a period. The period, and like they say, a period in microseconds for 1 second here. Well, 1 second in microseconds is a million, right? Because it's -6, right? So a million microseconds is 1 second. And then we're defining the crystal, what the internal oscillator is. Now, we're not setting the oscillator because it defaults to 4 megahertz anyway, and that's the only internal oscillator we have. So we're gonna do this. So we've got that set up. We're gonna define our period of instruction clock in microseconds. So it's gonna be 4 times our 1 second divided by whatever our crystal is. So basically the period's gonna be 1. Then we're going to say, okay, timers, we're going to input as a defined. I'll show you why, because we're going to do a bunch of calculations here later. But we're going to take the timer 0 prescaler, okay, which are prescalers. Okay, what the prescaler is going to do. Okay, and okay, you know what, actually, I think what I'm going to do is I'm going to show you this in an Excel spreadsheet that I had made previously. Let's boogie this over here real quick. Okay, this is what I got going on here. In fact, let's see, maybe we can minimize the, yeah, do like this. There we go. Okay, so we got our period. Our period is 1 calculated from here. Okay, our period of our period of instruction site in microseconds. Okay, so it's 1. Okay, we've got our scale. Our scale right now, we're choosing a prescaler of 256. We got our T0 ticks are 256, like we said, which that means it takes 256 counts in the timer before it overflows, okay, and sets a flag. So okay, so now we've got our tick period, which our tick period is going to be our scale times whatever our I period is, okay, and that's what the prescaler does. The prescaler scales your interrupt period. That's what they're declaring I is the interrupt period. We're scaling that, okay. So how long it takes before an interrupt occurs. So that's going to be, of course, it's going to be 256 microseconds. So it's 0.000256. You can see in the formula, I'm multiplying it, and I just divided it by 1,000,000, so that way it pulls it to microseconds. Okay. So now to calculate reloads, you need to take and perform this division. What you're going to do is you're going to take the period, what the period is, okay. So our main period, which is 1 second, and you're going to divide it up into how many ticks that is. So you divide it, and since our ticks are 256, it takes 256 ticks before it reloads. We're going to figure out how many total ticks a second is going to be. So you divide it by 256, basically. And so that's how many total numbers of ticks it's going to be to reach a second, or as close as we can get. Then, since you have this huge number of ticks, you're wanting to know how many reloads that takes to get there. So you're going to divide it by the ticks per period, which our ticks per period is 256 because it's an 8-bit counter, and 2 to the 8th power is 256. So we're going to divide it again by 256. And when we divide it again by 256, now that tells us how many reload periods we're going to have in 1 second. And here we get, and see, here's where you start getting off. We get 15 and a quarter, give or take. So now what it's going to do is it's going to, if you keep it in this formula like this, it will round it based on the 10th region, so it'll only round to 15. So that's basically 15, or you can just type it in. I'd rather type it in. I don't like to leave it up to this. I like to do my own rounding. So I would probably take this out and just type the number in. Once you see, this is a good roadmap to see how they're calculating it, but I do this type of a deal. But what I've done in this Excel spreadsheet is I've set this up where it basically does this. All these are basically variables, so you got 256 and 1, and then this one is 256, and then this one multiplies these two together and divides by that, and then this one takes 1 and divides it by the B3 is 256 and B4, which is that, and that's where we get the 15. And in doing this, I can then play with the scale, and I'll show you here in a minute. Now, if we invert this back, let's say it is 15. we hard set 15. Well, let's go the other way around and see, okay, if we have 15 reloads, how close to a second is that? And that's what this calculation does. If we have 15 reloads, okay, so that means if we had 15 times 256, or times 256 microseconds, then that is going to have to be times our B3, which is 256 ticks. Okay, so that's what we're doing, is we're doing 256 microseconds times 256 ticks is one reload. Okay, then we're going to multiply it by 15 reloads. Okay, so that's where the 15 comes from. So first we have 256 microseconds times 256 ticks in a reload, and then we have 15 reloads worth. And then that gets us to about 0.98304. Okay, so it's almost a second, but it's still off. It's off a few hundredths of a second. Okay, quite a few hundredths of a second. And again, like I say, that may add up over time. So see, you can see the difference is you're off, basically you're off 16.96 milliseconds is what you're going to be off. So, but if you take 16 milliseconds, okay, let's do this real fast. Let's do this math. So if we take 16, or 0.016, or let me get a scientific calculator going here. If we have 0.01696, we have 16 milliseconds, okay, that we're going to be off. And if we multiply that by, let's say, 60, because it takes 60 seconds to equal a minute, we're going to be off at least a second. In 1 minute's time, we're actually going to show that we're actually 59, or actually 58.9 something seconds is what we're going to show, when actually it is a full 60 seconds. So we're going to be off a little bit. Now, if we keep going with this, let's clear this out, 0.01696. If we keep going, we go 60, and then 60 again. Wait, I did that wrong, I'm sorry. If we go 0.01696, and then, or actually, oh, I did that wrong. No, I did that right. So we're 60 off, and then we're 60 again. We're actually going to be about a minute off. See, when we're a full hour, we're going to be a minute off in that hour. See, if you see that, we're going to be like a minute something off in that hour. So you gotta watch this. It can pile up on you. It looks really close, but it can pile up on you. So now you play with the pre-scaler, and if we can go back, let's see, I think I still have it. Yeah. If we go back and see what kind of pre-scalers we can play with, we got 128, 64, 32, 16, 8, 2, and 4. I found that 64 is the closest to a second. If you do the math, so when we put it in here, let's change this to 64. There. Now we're 0.999424. And we got 61 reloads. And we're now only, what would that be, a half of a millisecond. So we're 576 microseconds off. So that's really good. That's a lot better. And if we want to do our math again, and we're 0.000576 off times 60, yeah, see, we're only 34 milliseconds off. And then if we times 60 again, we're only about, yeah, like 2 seconds off. See that? We're only like 2 seconds off now. So see, it improved a lot. It's not perfect, but it is a lot more of an improvement. If you're wanting to go hours and minutes. Now, if you're wanting to do, yeah, like 20, 30 seconds, or you want to do maybe a couple minutes or so, if you're off 16 milliseconds, it's probably, or yeah, 16 milliseconds before with the 256, you may not care. If you're off 16 milliseconds, who cares? So that's something to play with. So that's a good formula to play with, and that way you can see how close you can get, and see like if we had 32, let's put 32 in here. 32 is pretty close too. 32 is about 500 off as well. So 32 is close. What about 16? 16 is fairly close. Let's get crazy. Let's do 2. 2 is really close. 2 is very close. So there's very precise. And then of course if we do 128, it's going to be off quite a bit. Yeah. So anyway, stuff to play with. So you might as well play with it. And so now let's get back to our coding. I know we spent quite a bit on this. I think what we'll do, actually, this video is really long already. Let's go ahead and stop here, and I'll create a part 3 to this, and we'll finish out the code.